Swayam Prabha. Digital India. Educated India.
Namaste. In this week, we shall start looking at volume computations. As you would remember, computation of the volume is one of the most essential parts of doing forestry, because whether we are doing forestry, whether we are managing our forest stands for say timber or for carbon sequestration or for any other means, in most cases we require how much amount of biomass is there in the forest, how much of it can be harvested, how much of it requires to be left in the forest, and so on. So, volume computations are paramount in managing any forest stand. Today, we shall start looking at volume computations through sections. So, these are known as direct calculations. So, we have done one example before. So, let us use this example to see how what we mean by direct computations. So, in this problem that we had done in a previous lecture, a tree has a height of 11 meters, its diameter at different heights is given, and we were required to calculate the volume of the tree. Now, this is the standard way in which a tree is cut for measurement purposes, and as we had discussed in that lecture, we divide our tree into a number of sections, in which the first section is considered to be of a length of twice of breast height, so that we could use the middle diameter or the diameter at breast height to compute its volume. The other sections were taken to be 3-meter sections, so that not only can we use this tree for the computation of volume, but at the same time it can also be used in a profitable manner by selling it. So, 3 meter is a standard section length, and the topmost section was considered to be a conical section. So, we computed the volumes of all the sections, and then we added up those volumes to get the volume of the tree. We also dealt with the volumes of a number of different shapes. So, now today we will look at an extension of those equations. So, as you would recall, the volume of a cylinder is given by S into L. So, we had earlier referred to this volume by this equation. So, in a cylinder, both the end sections are circular, it has a length of L, so it is, and it has a radius of R. So, we used to say that volume is equal to pi r square h. Now, in today's lecture we will redefine these terms. So, we consider the area of a cross section to be S, and we consider this height as the length of the solid. So, in this case, because the section is a circle, so S is equal to pi r square, h is equal to L. So, we can write that pi r square h is equal to S into L. So, that is the volume of a cylinder, it is S into L, where S is the cross sectional area of base and L is the height of cylinder, or we can call it as the length of the solid. Now, if we take a section of this cylinder, so let us take a section at this point. So, we have removed the top portion and we are now considering this section. So, this part of the cylinder is left. So, if we wanted to calculate the volume of this frustum of a cylinder, then also we could use the same equation, because this section and this section both are parallel circles. So, the cross sectional area here S will also be equal to pi r square, and now we can compute it for another length, let us call it L bar. So, in this case the volume will be given by S into L bar. So, when we are talking about a cylinder, so coming back to the slides, the volume of the full cylinder is or the volume of the full solid is given by S into L. The volume of a frustum of a solid is also given by S into L, where L now is the length of the frustum, and here S is the sectional area of the base and L is the length of the log or the length of the solid. Now, we also looked at a shape called paraboloid. Now, in the case of a paraboloid, the volume of the full solid is given by S into L by 2. So, if you remember, in the case of a cone, the volume was 1 by 3 pi r square h. In the case of a paraboloid, in the place of 1 by 3, it is 1 by 2. So, the volume of the full solid is given by S into L by 2, and the volume of the frustum of the solid, if we take Smolyan's formula, it is S1 plus S2 by 2 into L. So, in the case of paraboloid, now if this portion has a cross sectional area of S and this portion has a cross sectional, so let us call it S1 and S2, then the volume of the frustum of the solid can be taken as the average of both these areas. So, that would be the area of the cross section nearly of the middle of the solid. So, it will be S1 plus S2 upon 2 into L. Now, previously we saw that the volume is given by S by 2 into L. So, how can we correlate both of these? Because if we extend this solid such that both these ends meet at a point, so at that point your S1 will be equal to 0. So, then we will have, if we use this equation, it will be 0 plus S2, where S2 is the cross sectional area of the base upon 2 into L, which will be S2 upon 2 into L, which is the same as this equation. So, now this formula is known as the Smolyan's formula. Volume is the average cross sectional area of two ends into length of the solid. So, the average cross sectional area is given by S1 plus S2 upon 2 multiplied by the length of the solid. So, this is the Smolyan's formula. Now, coming back to the slides. So, here we have volume is equal to S1 plus S2 upon 2 into L. Now, in the top equation, in this equation, the S is the sectional area of the base. In this case, S1 and S2 refer to the sectional areas of the ends when we are taking a frustum, and L is the length of the solid. So, you must not confuse between S1 and S2. There is also another formula for paraboloid, which is known as the Huber's formula. So, this talks about the volume of a frustum of solid, and it is given by Sm into L, where Sm is the sectional area of the middle of the solid and L is the length of the log. So, if we drew our paraboloid, if the length is L, so this much is L. If we take L by 2, so we are dividing it into two parts. So, this one is L by 2 and this much also is L by 2. So, this is the middle point. So, at the middle point, if we take a cross section and we define this cross sectional area as Sm. So, Sm is the cross sectional area of the middle point of the solid, then our Huber's formula gives volume is equal to Sm into L. So, Sm here is the sectional area of the middle of the solid and L is the length of the solid. Now, coming back to the slides. So, this is the Euber's formula for a paraboloid. Now, let us consider a cone. So, in the case of a cone, we had earlier defined the volume of the full solid as 1 by 3 pi r square h. Now, pi r square is the sectional area of the base of the cone. So, if we drew a cone, so if this is a cone, with a height h and the bottom with a radius of r, then we define volume is equal to 1 by 3 pi r square h. Now, changing the notations, we can call the length of the solid as L and the cross sectional area of base as S. So, now cross sectional area of base is given by pi r square. So, in this formula we are replacing, so 1 by 3 pi r square can be written as S and h in this case can be written as L. So, now in this case L is not the slant height. So, earlier we had defined the slant height as this height, so this length. So, we had defined L is equal to square root of r square plus h square, which is the slant height. Now, remember that when we are defining this equation, this L is not the slant height, but length of solid. So, you must not confuse between this L and the previous L. So, now we can write the volume as 1 by 3 S into L. Now, what will be the what will be the volume of a frustum of a cone? So, what is the frustum of a cone? If we drew a cone again, and we are taking a section here. So, now this portion, so the top again is a cone, but this portion is the frustum of a cone. So, in this case we are removing the top portion. The top portion incidentally is another cone. So, the frustum of a cone is a portion of a cone in which its top has been cut to give it two ends. So, now if we drew the frustum of the cone again, so its top would be circular, the sides will be straight and the bottom edge will also be circular. So, this is a circular end, this again is a circular end. Now, we can write this, now both these ends have their own sectional areas. So, this sectional area is, so this is circular end of cross sectional area is equal to S1 and here it is the circular end of cross sectional area is equal to S2. Now, if L be the length of the solid, so if this height is equal to L, then the volume of the frustum of the cone. So, frustum of cone is given by V is equal to S1 plus S2 plus square root of S1 S2 whole upon 3 into L. So, we have taken both these cross sectional areas S1 and S2, you add them up then you multiply S1 and S2 and then take a square root, then you take all three of these, take the average. So, this is the average of S1, S2 and square root of S1 and S2. So, this is the average cross sectional area multiplied by the length. So, for instance, earlier we had defined the volume to be S into L in the case of a cylinder. Here it is S bar into L, where S bar is the average of S1, S2 and square root of S1, S2. Now, incidentally, if we extended this frustum to make a cone again, so in that case your S2 will be 0. So, what will be the volume now? Volume will be S1 plus 0 plus square root of S1 into 0, which is 0, upon 3 into L, which will be S1 by 3 into L. So, this will be the volume of cone. So, the volume of the cone is 1 by 3 S into L. Volume of cone is 1 by 3 S into L, where S is pi r square. So, by using this equation for the frustum, we can derive the equation for cone as well. So, this is one formula that you need to remember. The volume of a frustum of a cone is given by the average of S1, S2 and square root of S1, S2 multiplied by the length of the solid. Now, coming back to the slides again, when we talk about a neeloid, so neeloid is also a shape that we encountered before. So, here we define the volume of the full solid as 1 by 4 S into L. So, in the case of cone it was 1 by 3, in the case of a neeloid it becomes 1 by 4, and the volume of the frustum of the solid is given by Newton's formula by the average of S1, S2 and 4 times the middle sectional area divided by 6 into L. So, in the case of a neeloid, so S1 is taken to be the cross sectional area of thick end is S1, cross sectional area of thin end is S2, then we take a middle point and we take the cross sectional area of middle is Sm, the length of the solid is L. So, volume is given by S1 plus S2 plus 4 times of Sm divided by 6 into L, and this thing is known as Newton's formula. This is the volume of frustum. Now, if we extended this frustum such that it became a full solid with one end to be circular by the given by the cross sectional area of S and the other being a point with a cross sectional area of 0, then what would be the volume of the neeloid, complete neeloid? So, in this case, at around half of it will have the Sm will be roughly equal to half of S, and then will give the volume of the neeloid as 1 by 4 S into L. So, this is the volume of the full solid. Now, coming back to the slides. So, this was the Newton's formula. So, the Newton's formula, if you generalize it, it says that the volume of the frustum of a solid is given by the two cross sectional areas S1 plus S2 plus 4 times the cross sectional area of the middle portion. So, 4 into Sm divided by 6 into L. So, if we look at this formula in greater detail, This formula is one of the most accurate formulae which is used to find errors in the other formulae. So, the other formula are Huber's formula and the Smolyan's formula. So, Newton's formula is considered to be the most generalized and the most accurate of all these three. It can be used for the frustum of a needloid, cylinder, paraboloid and a cone. So, for all of these cases you can use Newton's formula. However, this formula is more cumbersome than the other two formulae, because here you are required to take 3 measurements of cross sections of both the ends and the middle. And in case your logs are stacked, so when we say stacked logs, we mean that this is your first log, then you have the second log in continuation, then you have your third log, then there is a log below this, then a log below these and so on. So, when you have this stacked stack of logs, so in this case taking the diameters of the ends is easy because they are accessible, but taking the diameter of the middle portion of a log is very difficult. So, taking a diameter here or measuring the cross section here becomes difficult because you do not have access to the central portion of the log. So, coming back to the slides, it is difficult to measure the mid diameter in stacked logs, which is why Newton's formula, even though it is the most accurate of all the 3 formulae, it is less used in the field conditions. Now, let us look at Smolyan's formula and try to generalize it. So, it states that the volume of a frustum of a solid is the average of the end cross sectional areas multiplied by the length of the solid. So, here in place of taking 3 readings, you are only required to take 2 readings of the end cross section. So, it is easy to use in the field conditions. And when you have a stack of logs, because you only are required to calculate the end cross sectional area, so you can just use a scale or a ruler to measure the diameter of the ends and to get these cross sectional areas. Smolyan's formula is accurate for cylinder and paraboloid, but it overestimates the volume by a small bit. The other formula that we looked at today is the Huber's formula. So, in the case of Huber's formula, it is defined as the cross sectional area of the middle of the solid multiplied by the length of the solid. So, in this case you are required to take only one cross sectional area measurement at the middle. But again, in the case of stacked logs, that becomes difficult because it is difficult to access the central part of a stacked log. It is accurate for cylinder and paraboloid, and unlike Smolyan's formula that overestimated the volume, Huber's formula underestimates the volume. So, now that we know that the Newton's formula is the most accurate formula, what is the amount of overestimation or underestimation in the other 2 formulae? So, let us find out the difference between Smolyan's and Newton's formulae. So, if you remember, the volume in the case of the Smolyan's formula, so Vs is given by S1 plus S2 upon 2 into L. In the case of Newton's formula, the volume is given by S1 plus S2 plus 4 times of Sm whole divided by 6 into L. So, what is the difference between both of these? So, if we take Vs minus Vn, we get L by 2 into S1 plus S2 minus L by 6 into S1 plus S2 plus 4 Sm, or if you multiply by 3 by 3, that is multiplying it by unity, we get 3L upon 6 S1 plus S2 minus L upon 6 S1 plus S2 plus 4 Sm, or taking L by 6 common. So, we have 3 S1 plus 3 S2 minus S1 minus S2 minus 4 Sm, which is equal to L by 6 2 S1 plus 2 S2 minus 4 Sm, which is equal to L by 3 S1 plus S2 minus twice of Sm. So, this is the difference between the Smolyan and the Newton's formula. Now, if we calculated the difference between Huber's and Newton's formulae, what would that be? So, volume by the Huber's formula is given by Sm into L. Volume by the Newton's formula is given by S1 plus S2 plus 4 times of Sm by 6 into L. So, if we calculated volume by Huber's minus volume by Newton's, what do we get? We get Sm into L minus L by 6 S1 plus S2 plus 4 times of Sm. So, multiplying it by 6 by 6 and taking L by 6 common, we get 6 times of Sm minus S1 minus S2 minus 4 times of Sm, which is equal to L by 6. So, we have twice of Sm minus S1 minus S2, or we can write it as minus L by 6 S1 plus S2 minus twice of Sm. Now, if you look at the previous page, here we had calculated the difference as L by 6 as L by 3 S1 plus S2 minus twice of Sm. So, let us write this portion as x. So, here we have the difference Vs minus Vn is equal to L by 3 into x. So, x is equal to S1 plus S2 minus twice of Sm, right. So, S1 plus S2 minus twice of Sm is x. So, putting it here, we have Vh minus Vn is minus L by 6 into x. So, what do we get here? We have Vs minus Vn is equal to, so here it was L by 3x, Lx by 3, and Vh minus Vn is minus Lx by 6. So, if this formula, if the first formula is overestimating the volume as compared to the Newton's formula, and remember that the Newton's formula is considered to be the most accurate formula. So, if the first one is overestimating, then the second one would be underestimating, and if the first one is underestimating, then the other one would be overestimating, because in the first case it is plus and in this case it is minus. So, today we had a look at the volume computation by the direct method, and we also looked at Huber's formula, Smolyan's formula and Newton's formula for different kinds of solids and frustums of solids. And we saw that if we considered Newton's formula to be the most accurate formula, the Smolyan's formula and the Huber's formula would bring out different estimations of the volume, which would be one, if one is overestimation, then the other one would be an underestimation. So, we can use these formulae to calculate the volumes of different sections of logs or of complete logs by themselves. So, thank you for your attention. Jai Hind.